and thank you for the invitation today. I'm very happy, I'm very pleased to speak here in person, that I don't have to speak electronically anymore. This is also for me something special again. Today, I would like to tell you something about the beginning and the future of the universe. The first question that you might have is, how did it all start? And what we think how it all started is that it started with a Big Bang. Now, what is this Big Bang model? What do we assume how it all has evolved? For that, I have found a nice colorful cartoon which shows an overview of the Big Bang model. And so I would like to guide you through this cartoon. Here you have the time axis moving up, and to the right you see the decrease in temperature, and you have here the temperature axis. Now on this side you see what has evolved, what type of particles were there in the universe, and you see down here at the Big Bang and right afterwards there are only question marks because we don't know exactly what went on at that time. And then yes, there are still particles with question marks in it, but later on we know about the particles when energy is decreasing slowly. We know about these particles from accelerator experiments. And later on, when it comes to protons, neutrons, electrons, these are particles that we are made of, that all our surrounding is made of. From then on, it is quite clear what happens. These protons, neutrons, they form, for example, helium nuclei, and then they form atoms by having electrons around, and then you form stars, and later on you have galaxies. So this is then the universe as we see it today. So this is a very short journey through the evolution of the universe. This is what we call the Big Bang model. Now you could say, oh, well, she is showing here a nice colorful picture. I can also draw a colorful picture and tell this is the universe, this is how the universe has evolved. I would like to show you now in the following that the Big Bang model is really a good model. I will show you several indications that it is a good model. I say not proofs. I can't prove that this is the right model, but there are several indications that this is really a good model. And so the question is, why do we assume that the universe has started with a Big Bang? And I would like to show you four indications, 4 hints that this is a good model. I will go with you through here these 4 pillars of the Big Bang model. There are many more observations. I just picked these 4 because I think they are quite convincing. So I hope that in the end you are convinced that the Big Bang model is a good model. Okay, now let's start with the cosmic microwave background radiation. What is this? I show you again the cartoon, because in this cartoon there are these red wiggly lines. These lines show photons, so particles of light that have been emitted at this time. Why here? Because here the energy has decreased so much that the light particles don't have enough energy anymore to rip off the electrons of the atoms. We call this ionization. Yeah, so before, when they had more energy, they interacted with the atoms, they removed the electrons, and the electrons came back, and so there was some interaction and some equilibrium, but it doesn't work anymore when these photons do not have enough energy. So at that point, the photons arrive at the atoms, don't interact, so they simply move on. And they move until today, and that is what we call that the universe is transparent, because these photons, they just move on, and we can still see them nowadays. They come from all sides, and that is what we call the cosmic microwave background radiation. microwave, because the energy has decreased so far now that it is in the microwave wavelength. Good. So, and this is what we call the oldest image of the universe, because this is the last time that these photons have been emitted with the last interaction with the matter at that time. And so we see the oldest image that we can see of the universe. And this looks like this. So it comes from all directions. And as this was such a breakthrough, when this was discovered, the Nobel Prize was awarded to these two gentlemen, Arno Penzias and Robert Wilson. So they found this serendipitously. So they were working with this antenna, and they had a funny noise on this antenna. And they were so persistent, yeah, they tried to get rid of this noise, and they tried everything, and then they found it can't come from the antenna, it must come from the universe. It was predicted before that this cosmic microwave background radiation must exist, and then it was brought together, and then they got the Nobel Prize for it. Now imagine you had a universe at the beginning that was completely homogeneous. You have if you have what we usually do, we look out of our Milky Way and galaxy density, and then you have regions here with very low galaxy density. So obviously the galaxies are not distributed homogeneously in the universe, not at all. And this is what we call large-scale structure. And this is something that would never have happened if the universe was homogeneous at the beginning. So, but fortunately, there were these small anisotropies that were found in the cosmic microwave background radiation. And that means in some regions there was a bit more density, and in other regions was a bit less density. And now you have gravity working. And that means there is attraction, the gravitational attraction. Some matter is flowing towards the regions that have had a little bit of higher density at the beginning, and the matter is moving away from the regions that had a little bit less matter at the beginning. And this is called gravitational instability. Yeah? You get higher and higher densities in one part and lower density. Other part you get. So this is increasing, and this is how large-scale structure is formed. Just to show you how this is, we have here a cube of early universe, let's say, and we do nothing but switching on gravity here, and then you see that gravity is at work, and you find that it forms these large-scale structures that we see nowadays. Good. This was the second pillar, large-scale structure, completely different from the cosmic microwave background radiation. And now we have something, again, very different. We go to very small scales. We go to nuclei. And here is a reaction shown how protons interact and end up as helium-4 nuclei. This is nuclear physics, and this is a very, very stable nucleus. So it likes to be in this state, and this is the reaction that takes place also in the sun, in the stars, and this took place also at the beginning in the early universe. And what happened then? Well, you could try to get another proton to this helium nucleus here. Unfortunately, then you have 5 nucleons, and this is not really stable. Or you could try to gather here 2 of these helium nuclei, and then you have a nucleus with 8 nucleons, and this is also not really stable. So it's basically, this is it, what happened in the early universe. No more fusion of elements. So now you can try to calculate how, with using everything that you know from plasma physics, from nuclear physics, and you know all the density, how it was in the early universe, the temperature, how it was, and how it evolved with time. Then you can start calculating what fraction of helium do I get, what fraction of proton, that means hydrogen, do I have in the universe. And then you do complicated calculations, and you end up with a diagram like this. Here in this diagram is shown again the time after the Big Bang, or equivalently again the temperature. So time is increasing, temperature decreasing. And here on the x-axis is shown the mass fraction of certain nuclei. And this is a very non-linear plot. So between one tick, there is a factor of 10. So when you start from the top, you see that already here you have just 1 in 1,000. So this is basically negligible then. So important is only the fraction that are here shown in the top, and also these elements that come here in very small fractions that are not so important now. You start with protons and neutrons, and then the fusion sets in, and you get a lot of these nuclei. And so this is theory. This is theory. This is all that we know. That we know about the physics and what we think is happening in the Big Bang model. And then you want to try to compare this with observation. Of course, you have to look in the right direction. You don't have to look where stars have polluted the universe, because stars form heavy elements. And so you must look far away from the stars, where you see the original fraction of helium and hydrogen. And there are such places. And when you do this, you find that the calculated abundances correspond exactly to the observed abundance. So this is another indication that the Big Bang model is a good model, because with the Big Bang model you find the abundances of elements in the correct way. So this was number 3. Again, something completely different to the other two. And now I come to number 4. Number 4 is the expansion of the universe. Of course, this is an expansion is what you would expect. When you have an explosion, you would have expect an expansion afterwards. So this was, was obvious that when you have an expansion, that you assume it could be an explosion at the beginning. So first question is, how do we know that we are in an expanding universe? So what do? We measure the velocity of galaxies. And we find that all the galaxies are moving away from us. And the further away the galaxies, the faster they are moving. This is a relatively simple measurement, because you can measure the velocity by the Doppler shift. The Doppler effect is something that you all know from the train or from an ambulance. That you hear it, that sound is different when the train is arriving or when it's passing and then moving away from you. You hear there is a change in frequency, and this change in frequency is, you know it in the sound, but this is the same also in light. So that means we can measure the shift in the frequency of spectral lines. And as this was such a relatively simple measurement, it was done already almost 100 years ago. You see here Edwin Hubble, who, after him, the Hubble Space Telescope was named, and he used this measurement to learn about the expansion of the universe. We have here in this diagram here the radial velocity that is relatively easy to measure, as I just explained to you. On this side is the distance of the galaxies, and this is not so easy to measure. what you see, what he found, yeah, the further away the galaxies are, the faster they are moving away. This is here the, yeah, and this diagram with a line through it. The slope here is the Hubble constant that is was highly debated, and this because it is used also a lot, because you just have to measure the velocity, and you know from the Hubble constant, from this relation, the distance of the objects. Decades ago, there was the groups have had a factor of 2 between their measurements, and of course this means quite a lot when you make a mistake of a factor of 2 in all your measurements of distances. Therefore, there were more and more measurements, and this is now shown from the year 2000 to 2017. You see that the errors were small, it became smaller and smaller, but it didn't always end up with the same value. So you have here, obviously, you use the universe as a whole, you use the cosmic microwave background radiation, and you end up with a bit lower values, while when you start measuring nearby distances and use them to calibrate the next distances, and so then you obviously get here the blue symbol, so a bit higher values. This is something, yeah, that is very strange, because it might point to certain things, that not everything is correct in our view of the universe. So not necessarily the Big Bang model, but there are many other things that we assume here, and this shows how interesting it still is. Yeah, there are still some discrepancies that might point to interesting things, and worthwhile to get even here more exact measurements. But nevertheless, now we go forward with a standard model. I just wanted to show you that there is more when you look at the details. So what we have measured is we have the slope in the Hubble diagram, and from this on we can calculate now some models. And I show you here some models of the universe. You have here the time. Here is the present time, the past. Here is the future. And on the y-axis, there is something like the size of the universe, or distances between objects in the universe. And we know 1 point. We measured it at the present time. We know here the distances between objects from the measurements that I've just shown you. Now we would like to, so this is the only thing that we know. From this now we can make a lot of models. We can assume, for example, that there is a lot of matter in the universe. Matter means always gravitation. That means gravitational attraction. The matter is attracting each other, compensating for the expansion, and at some point the universe would collapse again if there was a lot of matter. If there is just matter so that this expansion would come to a hold, then we have the so-called critical density. Or if there is even less matter, then we are in the upper curves. Or if there is something else that acts as repelling, then we have other curves here showing like the green curve. So now we would like to know what is the future of our universe. And unfortunately, we cannot look into the future, not even with the largest telescopes that we have. This is simply impossible. But we can try to observe here the past. And this is possible because of the speed of light is finite. Yeah, when we observe distant galaxies, we see them in a state how they have been billions of years ago. And that means, when they have emitted the light, it was long time ago. And so in this way, we can have a look at the past and see how the universe was a long time ago. Good. That means we try to make some measurements here. From this, we see what is the model of our universe, and then we can say how the universe will go on. We can say something about the future of the universe. Okay, so obviously we need to measure distances because if we could just go to small distances, it doesn't help because here all the models are the same. So we need to go really a bit further out. That means to really distant objects, and we need to know on which curve we are. So we need to measure some distances out to very distant objects. How can we do this on large scales? And there is the so-called concept of standard candles. So you can imagine you are on a dark road and you see a light. The light could be a motorbike that is still far away, or it can be a bicycle that is already very nearby. And in this case, you better do not cross the road. So that means you need to know how much light is this emitting, and then you can judge how far away the object is. And this is the relation here. So the luminosity is how much light is the object emitting. Flux is how much of this light are we measuring. And you see that these two are connected by the distance of the object. So this is the idea behind that. So we need objects that have a certain, that emit light, so that we know that they emit always the same amount of light, and then we know how far away they are. Okay, what objects are we using? Hubble used variable stars. This is very clever because for certain type of stars, we know exactly how much light they are emitting. Unfortunately, stars do not emit a lot of radiation, so we can see also nearby stars, and we can't go to the large distances that we want to do. And therefore, other people have thought of other standard candles, and they came up with the idea of supernovae. Because supernovae are very bright. They can be as bright as a galaxy, as a whole galaxy for a short time. And in this way, a large volume could be measured. So now is the question, do we know the luminosity of the supernova? Do they all emit the same amount of radiation? Yes, there is one type of supernova that emits the same amount of radiation. And this is not a supernova where a core collapses, but this is a supernova that comes from a binary system. So you have here a white dwarf orbiting around a star, a red giant star that is so that this is inflating, so gas is moving from the bright star to the white dwarf. That means the white dwarf is getting more and more massive because there is always gas accreting there. And at some point, this white dwarf is not stable anymore. At some point, there's simply too much mass, and this white dwarf is exploding. And it happens that this so-called critical mass is at 1.4 solar masses. So this happens when the white dwarf has 1.4 solar masses. And then, it is always the same amount of matter that explodes. The explosion develops always in the same way, and that means the supernova emits the same amount of radiation. This is the principle. Of course, when you look at it closer, it is not so simple. It depends a bit what the element this white dwarf is made of. It might be that not all the radiation reaches really us, that there are some gas and dust in between that takes away some of the radiation. So that are the details that make this really difficult to measure. But in principle, it is possible to use this and of course, you have to observe supernovae, where you don't know where they go off. Yeah, they can be anywhere in the universe, so you must monitor parts of the sky and hope that such type of supernovae explode. And some people did that. And they did that work there for many years. Many people worked for many years. 2 different groups have done this, and it was worth the effort because they got the Nobel Prize for it. And so what did they measure? This was really a breakthrough in the year 99. I show you again the diagram as we have seen it before with all the curves. They have now shown this in different colors, but it is the same diagram. You see here is the time, and here is today, and here is the distance. And then they have measured here certain supernovae. So when they measure supernovae not far away, you see that it doesn't help a lot. You cannot distinguish the measurement. But when you go out to larger distances, you find that the supernovae are always on the uppermost curve here, and this curve was in our diagram this green curve, and this green curve says that the universe is having an accelerated expansion. So at that time in 99, this was quite something, because nobody expected that. It was more at that time, that we are here in the critical density, low density, somewhere there, but an accelerating universe, that was quite a shock. Fortunately, there were 2 groups who did these measurements, and they got the same results. And this is always very good, because then you can be quite sure that it's reliable, and it has also always been confirmed afterwards. So obviously there is not only matter in the universe, but there is also something that acts in a repellent way, and this was called dark energy. And now we want to have a closer look, at how much of matter how high is the matter density in the universe, how is the dark energy density in the universe. We want to know how much of this attracting part do we have, how much of this repellent part do we have. So how can we measure these quantities? For this, we start with the matter density. That's a bit simpler, but again, you can't do it in the way you would do it at first. You could add up all the visible light that you see, for example, all the light that galaxies are emitting, and then you find, that doesn't work. Obviously, there is not only luminous matter in the universe, but there is also some component that is not luminous, and that is called dark matter. That makes it difficult, because we cannot observe dark matter directly, so we have to use indirect methods. And for this, we use, for example, galaxy clusters. Why do we use galaxy clusters? Because they are so huge, and they have collected matter from a large fraction, or many megaparsecs around them. They have collected all this, and all this is together in their potential well. So we have, and the potential well, everything that falls into a galaxy cluster, it doesn't matter whether it's luminous matter or whether it's dark matter. So that means you should have the same mix in a galaxy cluster that you have also in the universe. So a galaxy cluster is assumed to be representative for the universe as a whole. And now I would like to show you here's some methods how the mass of such a galaxy cluster can be measured. Also here, you could make errors when you use just one method. So it's always good to have several methods and then see whether it's consistent, whether the results are consistent. So the first method that was used is motion of galaxies. Then we come to the intracluster medium, that is gas between the galaxies, and also a very interesting method, gravitational lensing. Good. We start with the motions of the galaxies. The galaxies are moving around in such a cluster. We can again measure this with a Doppler effect. Relatively simple measurement. We see that they are shifted. Some are moving away from us, some are moving towards us. So everything is swirling around here. And as this is you get usually a distribution of velocities, and you have here a standard deviation, and the wider this velocity distribution is, the larger is the mass. So the standard deviation is a measure for the mass. And as this is a relatively simple measurement, it was done already a long time ago, used by Fritz Zwicky in the 1930s. And he found already that there is something wrong. There is I can't see all the matter, and he called this missing mass problem what we nowadays call dark matter. But he realized already there is something going on in galaxy clusters, so not everything is visible. Good. Now we come to the second method. We can measure the mass of galaxy clusters via the intracluster gas. So there is gas between the galaxies, but you were not able to see this gas because it was an optical image that I showed before. And this gas is very hot. This has temperatures of 10 to the 7th to 10 to the 8th Kelvin, and that means it emits the light in X-rays. And X-rays cannot pass the atmosphere. Good for our bodies, but it's not good for X-ray astronomy. So X-ray satellites have to be put into orbit, and X-ray telescopes are on the X-ray satellites. So for example, of course, I have to show here some satellites when I'm at ISSI. And there were done many of these observations of this intracluster gas. And here is an example of how the gas distribution compares to the galaxy distribution. This shows the Virgo cluster. This is the nearest cluster to us. And you see here some galaxies, this negative picture, here 2 prominent galaxies, for example, and a number of other galaxies. And this is the same in X-rays. This is in false color, but you see also here are these 2 prominent galaxies. You see them here as maxima in the X-ray distribution, but you see X-ray distribution everywhere. So everything here is filled with this hot gas. You just need to look in the right wavelength. And now you can use this also to infer the mass of such a galaxy cluster. You can measure the density of the gas. You can measure the temperature of the gas and all the distributions. And from that, you can say how is the size of this potential well, what is the depth of the potential well, and this tells you the mass of such a galaxy cluster. Okay, this was the second method. So we do a completely different measurement. In the first one, we measure the velocities of galaxies. Here we do X-ray observations of the gas. And now the third measurement is again something completely different. And for here, I show you again this cluster. And in this cluster, you have here galaxies that belong to the cluster. These are these diffuse yellow objects. These are all galaxies that belong to the cluster. But when you look closely, you see that there are some funny things here, the elongated structures, the blue structures that don't look like the other galaxies. And obviously, they don't belong to the galaxy cluster, but this is something different. And when you look at this might remind you of optics that you had at school. You have here to the left the observer. Yeah, here is the Earth, here is the telescope. In between is some kind of lens, and here is a distant galaxy that emits light. Now, what happens? The light is influenced by the lens, only that this is not a glass lens that as we use it in optical, but this is a lens that acts because it is so massive. Yeah? All the mass is here influencing the light, so the light is bent due to the high mass of this galaxy cluster here. And what you observe then from Earth, you see, for example, a signal in that direction. So you would think it is here, the source of this signal, but it is not. But it is right behind the cluster, and actually it was bent here at a certain angle, and you can have a second image of the same distant cluster, a distant galaxy, for example. Also here you see that the light is bent, and the more massive the cluster is, the more bend, you see it in the angle here. And so this angle is again a measure for the mass of the galaxy cluster. So this is again a completely different method. And now we want to compare all these three different methods. Also here, I tell you just the principle. I don't tell you how nasty it gets when you do the actual observations, because you probe actually different volumes, and you can also here have some errors. But I don't want to go into details this today. I want to show you just the general picture. So the results by all methods is that there is about 4 times more dark matter than visible matter in the universe. So a lot more dark matter than visible matter. And in this way, we can measure how much of this dark matter is in the universe. All methods show basically more or less the same result. Good, we can trust it. Yeah, if three different methods show the same result, we can trust it. This is now a summary of the dark matter. By far, most of the matter in the universe is not visible. Dark matter has to be there to make galaxies bound, to make galaxy clusters bound objects. Yeah, if you wouldn't have this dark matter, the components would move much too fast, and these objects would disperse immediately. So here is the stars that move too fast, and soon you wouldn't see any galaxies anymore. And the same is true also for galaxy clusters. Yeah? It's moving so fast that if they wouldn't be bound together by the dark matter, they would disappear immediately. Dark matter is also around us, also in this room, by the way. It's just that here it's homogeneous, very distributed very homogeneously. You don't feel the gravitational attraction because all the forces compensate, but it is also here. And interesting fact is that we still don't know what it is. So it's probably elementary particles, and there are many experiments going on trying to find candidate particles for this dark matter. Good. This was dark matter. Now we count how much of this dark matter do we have, and also there is such a lot of dark matter there. It is not enough matter in the universe to turn around the expansion. It is not even enough matter there to bring the expansion to a halt, but there is only about 30% of the matter there that would bring the expansion to a halt. And we call this then always this omega matter is 0.3. This is our nomenclature for this. So with all these searches for dark matter, we haven't found enough matter to bring the expansion to a halt. This is already an interesting result. Now we come to this other dark component, the dark energy. This concept is not so new. It was already introduced by Einstein in his equations, because Einstein thought at that time that he is living in a static universe. So he needed a term to compensate for the gravitational attraction. Yeah, he thought, well, there is all the matter. If I don't have a term that is somehow repellent, everything would collapse. Only later it was discovered by Hubble and others that the universe is expanding. And then Einstein thought, well, this was my greatest blunder. I don't need an additional term here that he called cosmological constant. By the way, we still use his lambda, as we say this omega lambda here. So he said, I don't need anything that is repellent, because we are not in a static universe anyway, we are in an expanding universe. Unfortunately, he didn't live to see that it was not such a bad idea to introduce this lambda, because in 1999 it was found that the value is not 0 and that there is something in the universe that is repellent. Good. Also here, a short summary of the dark energy. It was introduced by Einstein and later rejected by him. But it is clear since 1999 that there must be dark matter in the universe, a lot of dark matter in the universe. Also here, it is not clear what it is, and there are many experiments going on to find, for example, the equation of state of this dark matter. And of course, the effect is that it causes the universe to expand, and that we have even an accelerated expansion in the universe due to this dark energy. Okay, now we also want to know how much of this dark matter is in the universe. And we go back to our cosmic microwave background we have seen already at the beginning of the talk. I pointed out that it is important that there are some anisotropies on this distribution here, but there is much more in this anisotropies than just that they are there. You can do some statistical analysis and complicated things, and when you do this, you find an interesting result. You find that the sum of these two quantities, the matter density and the dark energy density, they are 1. So the sum of these is 1, and as we know the omega matter, the matter density, we know that the omega lambda is around 0.7, and here is a historic diagram that tried to measure these different quantities. Supernova explosion, cosmic microwave background, clusters of galaxies, and interestingly, they all overlap in one point, and this is around these values as most probable values for the universe. And so I come to the end, and I would like to show you how we nowadays think that what the universe is made of, what are the constituents of the universe nowadays. In red, in this red sector, is normal matter. This is all the matter that that we usually study in physics, in chemistry, and we know a lot about this, but even there we don't know everything. And then comes here the blue sector of dark matter. Here we don't know what it is, and we're still very curious, and similar also for this huge sector in green for dark energy. And this is, there is still a lot to investigate in the universe, and there are many telescopes and facilities are planned or are being built at the moment that should bring some interesting lights for this diagram, for all the constituents of the universe. So it was a very interesting period for cosmology in the last decades. Lots of things have happened and lots has changed. And I'm sure with all the new facilities, we will get also very interesting results in the future. And with this, I want to close my presentation, and I thank you for the attention. Thank you. This is a good question. Why do we have so much matter and not antimatter? This is a principal question that obviously our universe consists only of nowadays consists only of matter. At the beginning, there was maybe some antimatter that has been then interacted with matter. There were also some measurements that tried to find some regions with antimatter, but whenever you have the border between matter and antimatter, you would see a lot of radiation as they interact with each other, and this wasn't found anywhere. So we assume that the universe basically consists of matter. There's a question, yeah, why was it set up in such an asymmetric way? We don't know.
Interesting how much we know today about the expansions, and it was very clear, or more or less clear. But do we have an idea what happened before the Big Bang?
This is a tricky question, and I usually refer this question to philosophers. This is something very difficult for physicists, because physicists always rely on observations, and we can't just look beyond the Big Bang. We can do just our observations closer and closer to the Big Bang to say, these were the conditions, and so, but we cannot look beyond. But the other colleagues might have an answer.
Mauricio, about the supernova type 1A. Normally we expect one every 100 years in our own galaxy, and when we are looking back and further, we see more and more galaxies. So I am expecting that this type 1A, type 1 supernova explosion are more and more if you look back and further. And I think the most further away has been measured with a redshift of 10.2 or whatever. How many do you expect to have 10 or even more or even less of these supernovas? Why would you observe also so less?
Well, it depends also on the region of the sky that you are scanning. Of course, groups, they always have a certain type, a certain region in the sky that they are scanning. And for this region and the the fraction of distant galaxies, I assume that they make then their predictions of how many they observe. If this number would be too low, then they probably wouldn't get observing time. So I assume that they get some reasonable numbers. Otherwise, it would be tedious, these observations. But I don't know. I'm not an expert on this, on supernova explosions. But I think it's just great that they were doing this. They are measuring the distant supernovas up to this.
Here in the front and then in the back.
Would you be willing to speculate which mystery will be solved first? The nature of dark matter or dark energy?
Well, speculations. Well, with dark matter, there are experiments that look for certain types of particles. And so I would speculate that first we find some interesting particles here. But as I said, it's just speculation.
Well, another question. Yes, again in the back, exactly.
It's maybe also a speculation, but what do you expect in the very, very, very far away future?
Okay, so everything is moving apart. That then there is no, at some point there is also no more gas left in the galaxies to form new stars, and then everything would be very boring, no new stars, no light anymore, everything is far apart. So I expect a very boring universe in the end. So I'm happy that we are living now where the universe is really interesting. Yes, definitely.
Of course, afterwards you have our opera also, and
Professor Schindler will be also our guest of honor, so we can continue asking, but this is not meant that we should stop now. Are there more questions? Yes, okay.
Has
Please.
there been made any progress on the nature of dark energy? Or
So what I know is that they that they measure the equation of state. That is what they are trying to find out. So equation of state. This is always how density, temperature, pressure are connected, and that is what they want to know.
Yeah, when everything will expand and more and more in 100 billion years, what will happen to the matters, to the atoms? Do they also neutrons and protons separate, and we will have only a mass of quarks?
I don't think so, because these are bound particles and they are still confined in the nuclei. So I don't think that they can be ripped apart.
There is no other question. I also had one. And this was when you showed these different theories how the extent of the universe may change, right? And if you look backward and you make the measurements, you see, okay, it fits the one which will not recollapse, which is even accelerating in the expansion. This is what we see in the past. On the other hand, we don't really understand the nature of the dark matter and the dark energy. So how sure are we that we can extrapolate from what's seen in the past into the future, given that we don't have a good understanding of what these things which are in play really are?
All colleagues are completely convinced, for example, that there is dark matter in the universe. There are alternative theories. I would dare to say that there are less and less of these theories, and more are convinced that there is dark matter in the universe. But actually, we don't see it. Yeah, it is, for us, it is like a model. It's the model that gives good results, that all the results are in agreement with the observations. But it is, you can also say, well, dark matter, this is a strange concept. It's not a concept that should be used by scientists. They should have a better concept, not such an idea of things that we don't see. It can be something else. I just tell you what are good concepts, what proofs we have, or what indications we have for these concepts. It might be that in 100 years, this talk is a completely different talk, and they say, well, at that time they thought about these funny dark things, and now we know it much better. Can be.
Thank you very, very much for this very interesting talk. Thank you very much.
Thank you.